Okay, so welcome to lecture 10. Today we will learn about a very popular machine learning method used to boost the performance of classifiers and regressors, generally predictors. Okay, so let's look at what we have here. So these are basically different samples. So we have sample 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 samples, and what we want to do, we want to classify those samples. So for now, as you guys can see, each sample belongs to R3. So we have only 3 features, okay? And here, these features are empty, so I'm going to fill them up, and our goal is to classify those samples. So let's say this is, this feature means it's equal to 1. Okay, it takes value 1. And if it's empty, it takes value 0. So this is quite a simple problem to solve. So, for example, I might have something like this. Okay, now, if I ask you guys to classify these points, you would see that it's a very easy task, right? So what is going on inside your brain? You just looked at those features and automatically thought about what? Those that have feature 1 activated, okay, should be put together. And those which have feature 3 activated should be put together. So this is the most intuitive classification by doing what? What did we do when trying to find a discriminative criterion to classify those? We simply compared what? The features, right? So we compare the features. So this is class 1, and this is class 2. And here we can say we have our classifier separating these 2 classes, okay? Good. Now, if we look at a different example right here. So maybe I have also the same samples, but I'm gonna play a little bit with the features. So here we will have something like this. Okay, so can you guys classify this into 2 groups? Do you feel that it is very intuitive and straightforward to classify these samples, these 8 samples, into 2 classes? No. Why is that? Can you, basically state why it's not very intuitive for our brains to classify the samples? And of course, if it's difficult for us, generally it's going to be also difficult for a machine learner, okay? So what are the issues? What's the first issue when you look at these samples?
Solution of these features is very different.
Very different. So there is a large variability in featural patterns, or feature distribution, basically. Okay. So also, just using your the naked eye, just if you want to put them together, if you stare a lot, okay, at those, and you really force your samples to go into 2 clusters or 2 classes, okay, because we're classifying here, for example, you will try to discover like some discriminative criterion according to which you're gonna put all of those together. For example, you would say if you have more than 1 feature activated, I can put them all together. So here you have more than 2, okay? And here you have only single features activated. So this is, one criterion. Another one, you can say if you have only 1 top feature activated, okay? Feature 1 activated. For example, these samples, okay? This is feature 1 also activated. Here 2. And this one, I'm gonna put them together, and the rest is just, that's it. That's my classification criterion, okay? So you can have different things, but it's not very obvious, okay? So now let's look at another example. For example, here, these are the same samples, but what did I do? I added more features, okay? So here I have 6 features, and if I add these, 3 more, I'm gonna have like 9 features, okay? Maybe I'll just do this before. And then if I keep on adding, right, what do you guys notice? Now, let me just put it right. Okay, so, and I add more. And generally, in real machine learning problems, you're going to have, a few samples, right, to train on, but very, very, like large number of features. Because, for example, if you have an image and your image has 600 by 600 or 1000 by 1000 pixels, you want to vectorize it, you're going to have, like thousands and thousands of features, okay? But you might have at the end just, hundreds of samples or 200 samples to train on. So now if you look at this case, right? Let's say, for example, I'm just making things, I'm randomly coloring features, okay? But there is a pattern, of course, to discover because we know that 4 samples of those, they belong to class 1 and another 4 samples belong to class 2. So we know that these samples should be different. But imagine if I have different values that the features are taking. So maybe this is, 0.9, right? So now you can see the patterns we're building complexity. So the higher the dimensionality of the features, okay, in your samples, the more difficult it is for you to classify, okay? So even now, if you look at this, for you, it's almost impossible to tell apart the, class 1 and class 2, okay? So this is generally what we call, in machine learning, it's a very famous problem, we call it the curse of dimensionality. Okay, data dimensionality. And also it's called high dimensional, small sample size data problem. So it means you have a small set of training samples to train your model on, but each sample has many features and you want to compare all of those and classify them, but it's not obvious, okay? So up to this point, in all what we have seen in the previous lectures, okay, we looked at, all features, and we just considered all features together to train a linear regressor or an SVM, linear or kernel SVM. And if we want to, for example, classify, if we look at classification, let's imagine that this is also a high dimensional feature a vector x, but I projected it onto a space. So here I can visualize the data and I plotted it against a label. So here, for example, if we want to classify or we want to fit a curve to the distribution of the samples, so this is, building a regression model, what we use so far is all the features, which means these are my training samples. I use all the features, okay? And then I have 2 classes here. I try to map each sample, so let me just correct this. So this is a sample, each sample to a particular value. So for example, if I'm classifying, it's a label, so this is, plus 1, etc. So this is class 1, and I want to map this xi sample to its yi label here, okay? So it's -1, -1, -1. So here, what is your F doing in all what we've seen before, guys? It's looking at all the features together and trying to kind of, map this long feature vector, okay? So we're mapping all of those features to a single output, but we're looking at all of them, okay? Great. So this is problematic. It has many issues. Now, what are the potential issues for this? If we want to train a classifier, F, okay, or a mapping that maps this high dimensional feature vector into a single value, a scalar. So imagine how many things we're doing to just shrink this long feature vector into one value, right? That tells us, based on those features, if this subject is, maybe disordered or healthy, or if this image has a face or a tree. Okay, so what are the issues if we use all features? So let's say there are three main issues. So generally when you think about building a model, whether it's a machine learning or from an algorithmic perspective, there are three things you want to think about. First is time, computational time of your model. Second is space, the memory it's taking, space complexity, time complexity, and also the complexity of the model itself, like generally. If you can solve a problem very well using a simple model, then it would be a better choice than having a very complex model that solves it too. Okay, so always opt for the simpler solution. Now, if we look at all of those features all together, I know that ultimately not all of those features are important for my classification task to train my learner. So the first thing is, if I choose to look at them all at the same time, consider all of them, so the algorithm will be generally computationally expensive. So it takes more time, okay, to find the solution. Why is that? I'm going to go back to this. So imagine, just saying, that this is my original data set, okay? And somehow, I trained my model and was able to classify with some accuracy. But then I know that specifically for this problem, okay, I know that these are the features that are most interesting, most important. So I could have solved it using just 3 features instead of using maybe 20 features, okay? Because these are the ones that enable me to tell apart the samples belonging in class 1 and class 2 from the samples belonging to class 2. So going back to this one, solving the simpler problem will be more computationally efficient. Now the second issue with this, when you have a very large feature vector and a small number of samples to train on, is space. Okay, so if you look at all the features, okay, you need more memory to store, more memory to store the data. Okay, so imagine, for example, your sample belongs to R 10 to the power, I'm just saying, of 4. Okay, so you would have many features and you need to store those. But believe me, if you are working on MRI data, for example, magnetic resonance imaging, images of brains, you have millions of pixels that you need to store. Okay, so that is not feasible. And imagine if you have thousands of samples times millions of pixels and you want to do classification. That is insane, right? So now I know with GPUs and all that stuff, you can still, circumvent that problem. But if you have a chance to make it easier, even if you have good resources to use, you want to minimize, you don't want to use those resources. You want to keep them, like, basically, how do I say, like, not use a lot of energy. So you want to solve your problem with least energy, even if you have awesome resources in your labs, okay? So the third one is complexity. So you want, if we will build a model that looks at all of those, right, your model might be complex, okay? Your model might be very complex. But if you, have a simple, like a smaller number of features, then your model will be simpler. So in this case, generally, I would say, if you look at all the features, you have a very large number of features, then the model will be, the trained or learned model will be more complex, okay? So now if we think about all of this, all of these issues, how can we solve this problem? Any ideas? So it's kind of pretty obvious, but I know most of you probably know this. But how can you potentially, solve these issues?
Reduce the dimensionality.
Yeah, reduce the dimensionality. That's it. So what we need to do, basically, we need to learn how to pick up, pick up the best features. So these are my features. I have D features here. These are my samples and samples. So if I learn to pick up or select the best features that will boost my classifier's performance, then I would better solve this problem, okay? So here, this is what we call, as you mentioned, dimensionality reduction solution. So for dimensionality reduction, feature dimensionality, of course, dimensionality reduction, because we have a curse of dimensionality, so we want to reduce or eliminate that curse by reducing the dimensionality of the features. So there are two approaches here. So the first one, the most intuitive one, is, let's say you have a d-dimensional feature vector. So this is your sample, okay? So this is my space. I have d dimension, dimension 1, 2, 3, etc. until I reach dimension d, okay? So this is a multi-dimensional, high-dimensional space, and I can represent each sample in this space, right? So here, to reduce the dimensionality, what I can possibly do, if I have some magic tool right here, I can learn how to select the best features, and this is what we call feature selection. So I can basically select dimensions, okay? The best dimensions on that will enable me to improve the classification. So basically, let's say dimension 1 and maybe 3 and 4 until 5 are the best to use to kind of, you know, like solve my problem. So in this case, I was in a high dimensional space, and then what I did, I reduced this to x belonging to rd prime, with d prime much smaller than d, okay? And in this example, d prime is equal to 5. And this is what we call a feature selection process or dimensionality selection process, where we're mapping a high dimensional, so we are mapping, okay, a high dimensional feature vector into a low dimensional space. Okay, so this is the first basically strategy. Now the second one is slightly different. So note that here, when we're doing feature selection, we're selecting specific dimensions. We know exactly what those dimensions are. Okay, so if we have our original matrix here, this is our training matrix X. We have n samples D. After learning this mapping using some strategy, okay, I know exactly the best features that I need to choose to reduce this, and at the end I'm going to have something like that, 5, only 5, and this is my reduced samples, okay, like the data. So I have n times what, d prime, and this is d. Okay, now the second technique is slightly different. So one possible way is also, you know, to reduce the dimensionality of this feature vector is not to select, but to extract features, new features, okay? Extract new representative features, but a smaller number, okay? So instead of selecting, we are projecting, okay? So here, it's projection based, so we can call it feature extraction. This is based on projection, okay? So for feature extraction, what we can possibly do is, you guys can imagine it like something like that. Let me call it project, okay? Map by projection. So I'm gonna have new dimensions. For example, I call it x1 new, or new features, x2 new, and x3 new. So these are my new dimensions. So I would project each point here belonging to RD. I will project it onto this 3-dimensional space. So my point here belongs to R3. Okay, so it's a lower dimensional space. Okay, so here, let's look at this. So these are completely different approaches, but they solve the problem. They reduce the dimensionality of the original features, okay? Now, let's look at a particular example. For example, these are 2 brains here. So in healthcare, we want to do classification. For example, we want to classify healthy and disordered brains. And in this example, we're representing each brain as a graph. So let's do a little bit of graph theory. So here, for example, I'm representing each brain as a graph. Okay, so this is the healthy brain, the map for the healthy brain, and then I have another map for the disordered brain. So these are two different labels, right? So let's say this is unitic plus 1, and this is -1. A disorder can be anything, so it can be dementia, Alzheimer's, autism, schizophrenia, etc. So what do I have here? So basically, I parcellate the brain into different anatomical regions. So this is, I call it region 1. Okay, and then I have another region. So let me put it this way. And then I have the yellow region, for example. Okay, so this is region 2. Right? And then I'll just take a third example, but you guys can understand how this goes. So I have another region, third anatomical region. And then in each region, I will create a node. So each region will be represented as a node in a graph. Okay? So here, the connection between the region, there are different ways of defining this and using, MRI data, magnetic resonance imaging. But you guys can think about this connection, for example, okay, or this thickness of the edge between these two regions as a similarity measure. So we want to see, if these two regions, if the pink and the yellow regions, on average, okay, if they are synchronized in functional activities, which means, for example, here at each, let me just zoom a bit. So at each pixel or at each vertex, if this is a surface, so this is the cortical surface, for example, we measure the brain activity. Okay, so this is what we call the blood oxygenation level dependent signal. The more oxygen you consume, the higher is the activity, right? So we're going to measure this in all of those voxels in this region. And then after doing that, you will average them. So by creating the average, you will have an average signal in this node, okay? So that's, how much oxygen your brain is consuming in that particular area in the brain, for example, okay? Then you're going to do that again for each region. So this is the mean bold signal. And then, for example, just saying, if you compute the correlation between these time series, four dimensional, time series signals, then you're going to get a value. So here the value, you will put it between, let's say, these two regions. So the pink one, the yellow one, so maybe a correlation of 0.9, which means they're highly correlated. Okay, and since this is an undirected graph, so since this graph is undirected, then what we can, we know that this matrix will be symmetric, right? Okay, so this is one measure. You can also measure the similarity in morphology, like take, for example, the average curvature of that region and the average curvature of this region and take their difference. So, curvature in region 1, region I minus curvature in region J, and take their difference. So this is a dissimilarity in morphology. Why, a dissimilarity in morphology is, dissimilarity is a good measure in morphology. So this might be a good feature because we know that generally if you have two brains, so for example, Alzheimer's disease, if you have two brains, okay, the healthy one, it will, so let's say this is the cortex in the healthy one, and this is the cortex in the disordered brain. We know that there will be a change in morphology. Some parts of the brain will atrophy, they will shrink, okay? So this change in the geometry, we can capture it. So this can be a good feature to tell apart the disordered from the healthy subjects, okay? So that's why modeling the similarity or dissimilarity in morphology, not just in neural activity, can be a good feature to consider to perform this classification task. Now, going to this, right? So what we have here, what we want to focus on is basically these relationships. So I have also maybe no connectivity between these two. So I'm going to put 0 right there, okay? And the nodes that are connected to themselves, this is a self-similarity, so I can put 1s there, okay? Now, what is interesting, I'm going to just put some random values, right? So maybe 0.5 here, okay? 0.3, 0.4, 0.5. Now, if I look at the disordered brain, what I will notice sometimes maybe a dramatic change in specific values or specific connections, okay? And the thickness of those edges that encode the similarity between two nodes in the graph, in the brain graph. So this is, for example, right here. Okay, so 0.3. So it's a symmetric matrix, and this is what we actually call an adjacency matrix. So this is an adjacency matrix. I hope I spelled it right. Right? Okay, so this is an adjacency matrix for your graph. Okay, and this is for sample I, and we have for sample J. Now, what do you guys notice? You know, if we compare these two, okay, you notice that there is only one feature that is discriminative. Okay, so that's one single connection. So if we want to do feature selection, generally you might end up having just a few connections in the brain that are changed because of this disorder. So if the whole brain is, becomes abnormal, then the person will not be functioning, okay? So generally, a specific disorder will only affect very few features, not all the features. And this is why also from a biological and clinical perspective, feature selection is very important because it enables us to find, those, connections that went wrong in the brain, okay? Now, the second point is if we want to use projection, there is a key issue here. So what is the main problem? So let's say we want to perform feature selection, train a classifier, have a very good discrimination between these two cases, between these two populations, okay? Which dimensionality reduction method would you choose and why? Just intuitively. So we know the first one selects features, right? So we know exactly which features are most discriminative or enable us to, distinguish these two classes. The second method does what? It projects the features into a new space. So we only have new features. We don't know which these features, how basically what do they really represent, because we don't know that the new features we can map them back to these specific regions in the brain, okay? Once you project them, you are in a completely new space. You have new features. You don't know that your feature is exactly, that particular region or that particular connection in the brain. So if you think about it, projection is problematic because here, why it's problematic? It does not allow you to trace back the original feature. So if you're projecting, you're losing the original features. So it does not allow you to track the original features, okay? Because you are creating new features. Your new features might be good, well representative, etc., but you're losing the real information. So generally, if you're solving, a healthcare problem, you want to find some biological, some biomarkers, some biological fingerprints or discriminative features, you would go for feature selection methods, not projection-based methods, okay? So if your focus is on accuracy, you don't care about the features, you might try both. You might try, projection-based methods and then compare, feature selection versus, projection-based methods, and then select the best one. You don't care. But generally, we want in healthcare, we want to have both. We want to have very good classification accuracy, but also we want to find the good, most discriminative features so we can target them for potential treatments, okay? So this is just, to give you that generally people ask, now I know a bunch of feature selection methods and, feature extraction methods, which one to use? It depends on the problem, it depends on the data, okay?